in this crystal symmetry, we can write down the effective spin Hamiltonian for this honeycomb spin system. Here, Si is the spin at site I. The first term is the ferromagnetic exchange interaction between nearest neighbors, which is the strongest energy scale in the Hamiltonian. The second term is the spin-OB coupling term between next to nearest neighbors. Next to nearest neighbor means spin, these two pairs of spins, or these two pairs of spins. These are next to nearest neighbors. And nearest neighbors occurring in this ferromagnetic exchange interaction are these pairs, really two sides connected by one bond. So those are nearest neighbors. And the second term is the spin-OB coupling term, and sometimes it's called the Berezinskii-Kosterlitz-Thouless interaction. The last term is the G1 coupling of spins to the external magnetic field B. So all the honeycomb spin systems should be in this form because this Hamiltonian is written by requiring all the symmetry properties of this honeycomb lattice. And so this Hamiltonian is quite generic. So it's not unique to CLI3. So whenever you have a honeycomb spin system, this kind of Hamiltonian should be applicable. So in a ground state, all the spins are in the same direction like this. Elementary excitation from the ground state are spin waves as shown in this animation. And we can quantize this spin wave, and then we get a quasi-particle, which is called a magnon. And a magnon is a boson, and it carries a spin h bar, and the spin direction of a magnon is in the opposite direction of the spin direction of the ground state. So we have this effective spin Hamiltonian, and by performing the so-called Holstein-Primakov transformation, we can get a tight binding Hamiltonian for Magnon operators. Here, the I is the Magnon annihilation operator at site I. The I dagger is the Magnon creation operator at site I. And this first term is the on-site term. The second term is the hopping term between nearest neighbors coming from exchange energy. The last term is the hopping term between next to nearest neighbors coming from Berezinskii-Kosterlitz-Thouless interaction. So with this tight binding model for magnons, we can calculate the band structure as we can do in electronic systems. So here is the calculation result. We consider the quasi one-dimensional system. So here X direction is a periodic direction. So Kx is a well-defined quantum number. Along the y-axis, we considered about 30 sites. So this yellow box is our unit cell for quasi one-dimensional band calculation. And this is the band calculation result. So we have well-separated upper band and the lower band. And there are two modes connecting those two bulk bands. And if we take a look at the spatial profile of this blue mode, and we can actually explicitly see that these blue modes are localized along the bottom of the strip, and this mode, the Magnon mode, only moves to the right because the slope of this band is positive, meaning that it moves only to the right. So we have this kind of right moving mode localized well along the bottom of the strip. And this red line corresponds to the AtG mode moving to the left and localized at the top of the strip. So for the quasi one-dimensional band structure, we have two AtG modes counter-propagating to AtG mode. When we have a finite sample, then these two AtG modes should form one chiral AtG mode, rotating the sample in this way. So we theoretically predicted the existence of this AtG mode by calculating this quasi one-dimensional band structure of magnons in honeycomb ferromagnet in this paper. And it's numerically confirmed by certain micromagnet simulations. Here, researchers from China. This researcher is from China, and they considered this spins arranged on a honeycomb lattice, and they excited a single spin at the boundary with the frequency between this gap. So this frequency used for exciting this spin corresponds to one of these two AtG mode. In that case, excitation propagates along the sample, and we can see three features from this simulation result. First, it propagates only along the edge, and it doesn't go into the bulk of the magnet, right? So this excitation is localized along the boundary of the sample. Secondly, it moves only to the left without moving to the right, right? So it has a fixed chiral. Lastly, if you look at carefully, there are some geometrical defects here and here, which was made on purpose by researchers. And if you look at this scattering, then this excitation can go around this geometrical defect without backscattering. Normally, if we have this kind of defect, then when excitation interacts with this defect, there must be backscattering going to the right. Right? But because of this topological mode, topological protection, this excitation can go around this geometrical defect without any backscattering. So this is backscattering free AtG mode. And why do we have this kind of AtG mode? So we can understand that by calculating, by considering topological structure of Magnon bands. So this this right graph is showing the Berry curvatures of the upper Magnon band and the lower Magnon band, which is defined in this way. Here, UNQ is the Magnon wave function at momentum Q. So this is the so-called Berry curvature. It's like the effective magnetic field in momentum space. And this Berry curvature of the upper band is positive. Berry curvature of the lower band is negative. And when we integrate Berry curvature over the Brillouin zone, we get quantized number, like magnetic flux in real space. This integration of Berry curvature over the Brillouin zone is always discretized. And that's called the so-called Chon number. And Chon number upper band is turns out to be +1. Chon number of the lower band turns out to be -1. And when we have two bands with two different Chon numbers, there must be AtG mode connecting those two bulk bands, according to so-called bulk boundary correspondence, which is well-established theories in electronic topological phases. So this Magnon band is topological, and because of that topological nature, we identified honeycomb ferromagnet as a Magnonic topological insulator, which is analogous to the Haldane topological insulator, which was studied in this paper. So this bulk Magnon excitation mode was confirmed by neutron scattering by Pengchang Daiji group at Rice University in the US. So we have this upper band and the lower band, and there's a gap between these two bands. However, this neutron scattering does not tell us anything about topology, does not show us the Berry curvature. These are just the excitation spectrum. How can you see the Berry curvature? So we can see it by performing transport measurement. CRI3 is an electric insulator, so we cannot perform charge transport measurement, but we can perform spin and heat transport. So we propose the following experiment. Apply a temperature gradient to CRI3, then magnons will flow from hot region to cold region by thermal diffusion. If there are finite Berry curvatures for magnons, then magnons are expected to exhibit this kind of a Hall effect, Magnon Hall effect, generating a transverse spin current because magnon carries spin. And this spin current can be detected by the so-called inverse spin Hall effect. So this generation of a transverse spin current upon the longitudinal temperature gradient is called a spin-Lorentz effect, and it's quantified by spin-Lorentz conductivity. And so when experimentalists perform this measurement, if they observe finite spin-Lorentz conductivity as a function of temperature, shown as in this image, then that should serve as a experimental evidence for Berry curvature. of the Magnon bands in a honeycomb ferromagnet. So the previous example of this honeycomb ferromagnet is just it was the beginning of the discoveries of Magnonic topological insulators. So there are other Magnonic topological insulators that can be found in nature. For example, in this 2019 PRL, we showed that if you have a scomium crystal in magnetic systems, then magnons should exhibit topological phases in that scomium crystal phase. So this Magnonic TI in a scomium crystal is one type of Magnonic topological insulators that can be found in magnets. Also, recently, there has been expansion of this topological phase research into the topology of a hybridized mode, like, for example, Magnon-Phonon hybridization. So in this series of papers, we showed that although single Magnon band is topological trivial and phonon band is topological trivial, this Magnon-Phonon hybridized mode can exhibit non-trivial topology by their interaction. So that's called the topological Magnon-Phonon hybridization, and this is the one of the active research topics in the spintronics community. So why are we interested in these Magnonic insulators, Magnonic topological insulators? That's because these Magnonic topological insulators support this kind of a Magnon AtG mode along the boundary of the sample, which we can use as an efficient one-dimensional spin transport channel with no backscattering. So these Magnonic topological insulators give us very efficient Magnon transport channel that we can utilize in spintronic devices. That's the practical utility of these Magnonic topological insulators. So this is one of the hot topics in spintronics community. So second topic is about a magnetic Berezinskii-Kosterlitz-Thouless transition. So let me start. So this BKT transition can occur in two-dimensional XY system, and there are a couple of systems that can be classified as these two-dimensional XY models. The first example would be two-dimensional superconductor. I'm not sure you're familiar with this superconductivity, but when material enters into a superconducting phase, we have this kind of order parameter, complex wave function psi, which is the basically macroscopic wave function of Cooper pairs in superconductors. And psi is characterized by the two numbers. The first is rho, density of the condensate, and phi is phase of the wave function phi, here denoted by phi. So this phi can be arbitrary in a ground state of the superconductor. So, and this phi can be any angle from 0 to 2 pi basically. So we have an arbitrary phase in a ground state, and so that this phi represents the U1 degree of symmetry, degree of freedom of superconductors, but a ground state should choose one specific phi value. So, for example, from 0 to 2 pi, a ground state chooses arbitrarily one value from this circle. So, formally, we say that phenomena as a spontaneous breaking of U1 symmetry. So superconductors break U1 phase symmetry spontaneously. The similar example can be found in two-dimensional easy plane magnets. So let's say we have, let's say here XY plane is an easy plane for this magnet. Then in a ground state, the magnetic order parameter n will be in an arbitrary direction in the XY plane, right? And then we have this free parameter phi, which is the azimuthal angle of this magnetic order parameter in the XY plane. And a ground state should choose arbitrarily one of these points in the unit circle. So analogous to this superconducting case, ground state breaks the U1 spin rotational symmetry spontaneously in 2D Magnon easy plane magnets. So these two systems are very analogous from the symmetry-wise consideration. And in 2-dimensional superconductor, when there is a charge supercurrent, JC, this charge supercurrent is proportional to the spatial gradient of wave function phase phi. So when there is a spatial change of wave function phase phi, that means that there is a supercurrent flowing in the superconductor. The same thing happens for 2-dimensional easy plane magnet. When there is a change of this azimuthal angle phi in the magnet, that means that there is a spin supercurrent flowing inside the magnet. And these expressions are very similar. And so this spin supercurrent was theoretically proposed a couple of years ago, and there has been some experimental efforts to demonstrate this the presence of a spin supercurrent in certain material. For example, in this Nature Physics paper, graphene was used to realize this spin supercurrent. In this Science Advance paper, canted antiferromagnet Cl2O3 was used to realize the spin superfluid or spin supercurrent. However, previous research have focused on a very low temperature. At very low temperature, when for example, when T is 0, the magnet shows the long range. The spin is well ordered, like this. In a superconducting case, wave function phase phi is uniform in a ground state like this, and this is a well ordered state, and the superconductivity is present. However, this Berezinskii-Kosterlitz-Thouless showed that when the temperature exceeds the certain critical temperature, we have this kind of thermal excitations called vortices, like this vortex and this anti-vortex. These vortex and anti-vortex pairs are created spontaneously due to thermal fluctuations when temperature is above the certain critical temperature. And these vortices destroy superconductivity. So below BKT transition temperature, we have a good superconductivity. Above BKT transition temperature, we don't have a superconductivity. We have just a simple metallic phase. So there's a certain critical temperature called the BKT transition temperature. And formally, we distinguish these two phases with this correlation function. So when temperature is below this BKT transition temperature, this correlation function of the wave function phase phi or azimuthal angle for two-dimensional magnet, this correlation function decays as a power law with this power alpha when temperature is below this critical temperature. However, for very high temperature, this correlation function decays exponentially, very fast. So we don't have any long range order for high temperature. Below BKT transition temperature, we don't have like a real long range order. However, we have a so-called quasi long range order characterized by this power law decaying correlation function. So this phase transition between these two is the first example of a topological phase transition living outside the Landau's paradigm of a symmetry breaking phase transition. So there is no symmetry breaking between these two phases. However, there is a clear difference of correlation function between these two phases. So this is the first example of a topological phase transition. And due to this work, the Thouless Kosterlitz got the Nobel Prize in 2016. So how can you detect this BKT transition experimentally? It is not easy because first of all, it is not a symmetry breaking transition. So free energy is not singular at this transition temperature. So there are no clear thermodynamic quantities that can show this BKT transition. And secondly, two-dimensional XY materials are not easy to obtain. So you have to make superconductors really, really thin to be able to see this BKT transition. So it's not experimentally easy. However, fortunately, BKT transition has been detected for two-dimensional superconductors by resistance measurement. This Halperin, Nelson, and Doniak, Madison, Huberman, these guys showed that this voltage should be proportional to the I to the cubed power when temperature is exactly at BKT transition temperature. And when temperature is above BKT transition temperature, voltage should be linearly proportional to the current. So there's this change, abrupt change of this power alpha from 3 to 1, the temperature just starts to exceed this critical temperature. And that's how people measure this BKT transition temperature. So this is one of the experimental papers. Sample was PB, and here this is IV curve, and by in the log scale, and here then these lines corresponds to different temperatures: 5 Kelvin, 4.4 Kelvin, and 4.61 Kelvin, 4.12 Kelvin. And there's a line when ln V is proportional to 3 times ln I. So basically, V is given by I to the cubed power, right? At this temperature, and this temperature, 4.16 Kelvin, is exactly when BKT transition happens. That's how this experimentally we can see BKT transition temperature. The same technique has been used to detect the BKT transition temperature of this bilayer graphene recently in this Nature paper. So how about magnetic BKT transition? Superconducting BKT transition has been theoretically studied and experimentally observed. However, magnetic BKT transition have never been observed experimentally. That's because there was no two-dimensional X-ray magnet before. But since 2017, we have a variety of two-dimensional magnets, so we can now study BKT transition with these two-dimensional X-ray magnets. So how can it detect? Actually, we can use this similar technique. We can study decaying behavior of spin transport across BKT transition. So let me just skip this part. So when there's no vortex, then a spin should be able to flow through the two-dimensional X-ray magnet easily. But if there are vortices because of a high temperature, then spins scatter with the vortices, so spin should not be transported well when the temperature is high. So that's basically the mechanism for this magnetic BKT transition. On the theoretical side, we can formulate this superfluid story with this 2+1D dual electrodynamic formulation. We can write down this kind of Lagrangian in terms of vortices and spin waves. And we can do some research. So if you are interested in details, you can look up this theoretical paper. So in a nutshell, when the temperature is below BKT, so this inverse spin Hall voltage is given by the power law of this length of the two-dimensional magnet. When temperature is above BKT transition temperature, this voltage, inverse spin Hall voltage, will be exponentially expressed as this length increases. So there's a functional difference of this inverse spin Hall voltage as a function of the length of the magnet. So that's how we can detect magnetic BKT transition. So, but there were another proposal for metallic X-ray magnet. So by measuring the resistivity change across the BKT transition temperature, one can observe magnetic BKT transition too. And then, so let me summarize my talk. So a two-dimensional EGX magnet can support this Magnonic topological phases, which involves this Magnonic etch mode that can be utilized in spectral devices. Two-dimensional EG-plane magnets exhibit magnetic BKT transition that is one of the first examples of a topological phase transition outside this Landau's paradigm for symmetry breaking transition. So two-dimensional magnets can exhibit intriguing topological spin physics, which cannot be found in bulk magnets and whereby offer exciting opportunities. So thank you for your attention.
Thank you very much for that excellent talk. Do we have any questions? I see Ajit has unmuted his mic. Do you have a question? Maybe not. Oh, he does have a quick question. Excellent.
Hello.
Hello.
Yep, hello.
Is it audible? Yeah. Hi, Professor Kim. It was a nice presentation, nice information. So I just wonder about your system. How do you distinguish between the spin orbit coupling interaction, and I mean the energy that relates to spin orbit coupling and DMI interaction? Because you have explained something like one term which explain the spin orbit coupling and the DMI interaction. So can you please elaborate on that? How do you distinguish between contribution from the spin orbit coupling and DMI interaction in your 2D system?
Yep.
I suppose my question is audible. I mean,
Yeah, that's fine. Thanks for the question. And so I wrote down this spin Hamiltonian, right? And I guess you are referring to this second term, right? So this second term is a spin orbit coupling term, because the reason is the following. Here, these are SI, SJ, these are spins, right? And here, nu ij is orbital degree of freedom. So nu ij means that from when let's say this guy is I, this guy is J, and when you go from I to J, then we have to take left turn or right turn. We have to take either left turn or right turn, depending on the position of J. So when we take left turn from going from I to J, then nu ij is +1. When we have to make a right turn to go from I to J, the nu ij is -1. So meaning that this nu ij includes the orbital, in other words, the spatial degree of freedom. So nu ij represents the spatial degree of freedom. Si is spin degree of freedom. So these two are mixed in this single term. So in that sense, this is spin orbit coupling. Spin orbit coupling. So, and then for some historical reason, it's also called the Berezinskii-Kosterlitz-Thouless interaction.
Okay.
So without spin orbit coupling, there will be no this term. Yeah, without spin orbit coupling, there will be no second term.
And another thing, like as you know about Skyrmion, like spin orbit coupling, you need a high strength of spin orbit coupling. Let's say tantalum, iridium. So that induce the high strength of DMI interaction. So in your CR-I3 is like spin orbit coupling is everywhere. I mean, it will be there. So that's what I was expecting. If you can separate these two terms, like kind of addition of two terms, spin orbit coupling and DMI interaction. So I'm not sure of what I'm saying, but I was thinking if you can have two different terms for the spin orbit coupling, because yeah, that's what I was thinking. Yeah, you explain in the nice way. That is helping. Yeah. Thank you.
Well, I would just say DMI is one of manifestations of spin orbit coupling. They are not different things. Yeah, DMI is one manifestation of spin orbit coupling.
I see. Okay. Thank you.
Yep. Thank you.
Okay, I think unfortunately we are out of time for questions. So if you have any more questions that you wanted to ask but didn't get a chance to, please either ask them in the chat or in Gather Town. And